And I just want to take a couple of minutes to go over the project prompt. All right, it's a manufacturing application problem. It says, note, in this project, you will use the simplex solver. So you'll need to use that website that we've been using. You should include the input and output from this solver. You can do this by copying and pasting the functions from your computer. So that means I should know what you typed into the solver, and I should know what you got out as your optimal solution. All of that should be included in your project. You don't have to add all of the like the matrices that come at the bottom. You don't have to include that information. Just the setup that you typed in and then your optimal solution. All right. The Kimball Firefighting Equipment Company makes alarm valves. It has 2 assembly plants, Plant A in Atlanta and Plant B in Buffalo. Plant A can produce at most, can I highlight things here? Oh no, it's not a PDF, so I can't write on this, which sucks, that's bad. It's a document, but that's okay. Plant A can produce at most 8,000 alarm valves, and Plant B can produce at most 10,000 alarm valves. The cost to produce an alarm valve at Plant A is $12, and at Plant B, it's $18. All the alarm valves are produced and shipped to 2 warehouses, one in Pittsburgh and one in Savannah. The grid below shows the distance between these locations. So it's 685 miles from the Atlanta plant to the Pittsburgh warehouse, but 248 miles from the Atlanta plant to the Savannah warehouse. And then 215 from Buffalo to Pittsburgh, 907 from Buffalo to Savannah. Okay. And then currently the cost per mile to ship is 3 cents. Okay. So the first thing you're asked is to calculate the total cost to produce and ship alarm valves from each location to each warehouse. So there are 2 locations, 2 plants and 2 warehouses. So there are 4 unknowns that we have here. The cost from Atlanta to Pittsburgh, then Atlanta to Savannah, and then Buffalo to Pittsburgh and Buffalo to Savannah. So you should have 4 unknowns, okay? And when calculating that cost, you should include the mileage that's given here. So if we know that it's 685 miles to get from Atlanta to Pittsburgh, and we know it costs 3 cents per mile, we can multiply those 2 things together, right? That'll tell us how much it costs to ship, or just the distance, how much it costs to ship one of the valves. And then also you have to take into account the cost that's up here. And it's also gonna cost us $12 to produce an alarm valve at Plant A, $18 at Plant B. So taking into account all of that information, in Plant A, it's $12 to produce the valve. And then for shipping, it's gonna be 685 miles times 3 cents. Multiply all of that together, and that'll give you a cost from shipping a valve from Plant A to warehouse 1. And then you wanna do something similar for A to warehouse 2, B to warehouse 1, and B to warehouse 2. So you should have a cost function that has 4 terms and 4 unknowns, okay? From there, you can set up your constraints based on 2 things. One, up here, it says Plant B can produce at most 10,000 valves and Plant A can produce 8,000 valves. So you'll be able to set up 2 inequalities using that information. And then also in part 2 here, it says the demand for alarm valves from warehouse 1 is 9,000 and at least 6,000 from warehouse 2. So with that information, you can set up inequalities. And then once you have your cost function, your constraints, put this into the simplex method to solve. All right, that's the first part. And then all that's different for the rest of the problems is you end up changing the cost per mile. So you'll repeat this problem, but instead of having 3 cents per mile, it'll be 5 cents per mile. So it's basically just setting up 1, 2, 3 linear programming problems where you change the cost per mile each time. Okay, and then for the last question, it's saying that we plan to shut down one of the plants, the Buffalo plant, and you want to see how that affects the cost and if it's worth it to shut down that plant. Will that lower your cost overall? So if you have not looked at this already, please be sure to start on it. As always, as you're working on your project, if you run into any issues or have questions, you are welcome to come and ask me questions. You are also able to go to the Math Lab tutors. They should help you or be able to help you with this as well. Next, actually, before I cancel, I'm going to go back to modules. We are all done with the Unit 2 module other than Project 2. And then we can move on to Unit 3. In Unit 3, we cover the last two chapters, chapters 5 and 6. In chapter 5, we talk about exponential and logarithmic functions. We're going to spend about 4 classes going over these things. Today, we're going to introduce what an exponential function looks like, what its graph looks like, shifts, vertical and horizontal shifts of exponential functions, the domain, the range, and then modeling with exponential functions. And then hopefully we'll have time to get to logarithms also. We'll see. But we'll introduce logs also possibly either today or tomorrow. Logarithms are the inverse of exponential functions. So we'll talk about that. And then chapter 6 is my favorite chapter. It's about finance applications. So we talk about compound interest, annuities, loans, mortgages, car pay. Well, do we talk about car notes? You can talk about car payments, but things like that. If you're making an investment into a compound interest or in compound interest problems, or an investment into an annuity, or you're getting money from an annuity, how we can calculate how much you get. Okay, so that's my favorite chapter. And then we'll be all done. So look, this is the last little bit. We're 2/3 of the way complete. Last little bit to go. So to start today's class, before we go to the lab, I want to just write up the definition of what an exponential function is, sketch a couple exponential graphs, talk about shifts. We'll do all of that on the whiteboard in Zoom. See if I can find it. Surely I can find it. There it is. All right, so this is chapter 5, section 1. So section 5.1, exponential functions. And we'll start off with the definition. What does an exponential function look like? An exponential function is of the form f of x equals c times a to the x. So c times a to the x. So an exponential function is of the form f of x equals c times a to the x, where c is a constant, any real number, and a has to be a positive number greater than 0. So we'll say where a is greater than 0 and a is not equal to 1, because 1 to any power is just 1, so that's not very interesting. And c is a real number. So this is an exponential function because our variable x is in the exponent. Okay, so when our variable is in an exponent, we get an exponential function. We have a special name for a. A is called the base. Of the function. And also, we'll see this a bit when we graph. So a is the base, and 0, c will be the y-intercept. All right, so I'm gonna just write out a couple examples of what exponential functions would look like, and then we're gonna talk about what the graph of these types of functions will look like. And when we graph them, we need to know the shape of the graph, the domain and the range, and then also the intercepts and the asymptotes of the graph. All right, so examples of exponential functions. Basically, we're taking any positive number and raising it to the x power and then multiplying. So something like 4 times, sometimes I use parentheses, 1.5 to the x power, y equals, or y equals 1/2 times 3 to the x plus 2. It's an exponential function. Y equals 3.12 times 4.31 to the x minus 5 power. These types of functions take any number, any real number, times some number bigger than 1 raised to a power. The biggest thing here is your exponent, the x value, your exponent contains your variable x. That's what makes it exponential. All right, now for my favorite part. So we said that our base A has to be a number that's bigger than 0, but not equal to 1. We get two basic shapes for the graph of an exponential function, depending on whether or not A is greater than 1 or A is less than 1. So we'll start off by looking at graphs where A is bigger than 1. So we're going to graph y equals c times a to the x for A greater than 1. When A is greater than 1, we end up getting an increasing function. So you're taking a number bigger than 1 and raising it to different powers, like 2. 2 to the first power is 2, then 2 to the second power is 4, then 2 to the third power is 8. As the power increases, the function increases, the output increases. So for exponential functions of the form c times a to the x, when a is greater than 1, we get a function that starts off really close to the x-axis, and then it increases really, really quickly as x increases. Okay, so it's an increasing curve like this. Important characteristics. We said that this point here, where the graph crosses the y-axis, it's going to be at 0, c. Okay, and then some important characteristics here. First, the domain of this function. Remember, domain is all of the possible numbers we can plug in for x. I can take a number and raise it to any power. The exponent can be any number, positive, negative, decimal, fraction. So the domain is all real numbers, which we denote with interval notation, negative infinity to infinity. However, for the range, let's think about this. We're taking a positive number and raising it to different powers. Is it possible to take 2 and raise it to a power and get a negative number? No, it's not. Even if you raise 2 to a negative exponent, 2 to the negative second power, that's just 1 over 2 to the second power, which is 1/4. It's a small number, it's a fraction, but it's still positive. Because of this, our range can never, or our outputs, I should say, can never be 0 or negative for these types of functions. So we have 0 to infinity for the range. I'm just going to erase this little 2 thing. And actually what's happening at the x-axis is we end up getting a horizontal asymptote. The graph, as x gets more and more negative, gets very, very close to 0, but it doesn't actually touch 0. We'll do an example by graphing 2 in just a second. So we have a horizontal asymptote. At y equals 0. Y equals 0 is the x-axis. And then last thing, we wrote it on the graph. Let's write it down here also. We have a y-intercept at 0, C. This is true for any exponential function of this form. If you take a number times another positive number raised to the x power, the graph looks like this. All right. What if instead of a being greater than 0, we had a being something, a being greater than 1, we have something smaller than 1, but greater than 0. So next we're going to graph same function, y equals c times a to the x, but this time for a values between 0 and 1. So if you have a base that's like 1/2 or 1/3 or 3/4, a fractional base, or 0.87, a decimal that's smaller than 1. In this case, you end up with a decreasing function. Okay, boom. So in this case, your graph would start off really, really big, and then as x increases, y decreases and gets closer and closer to 0. But again, it never actually equals 0 or becomes negative. And then here's the interesting part, my favorite. In both cases, whether a is bigger than 1 or a is between 0 and 1, the domain, the range, the horizontal asymptote, and the intercepts are the same. The only difference is in one case, you get an increasing function, and in the other, you get a decreasing function. So in this case, the domain is still negative infinity to infinity. The range is still 0 to infinity. The horizontal asymptote, which I'll abbreviate HA, is still y equals 0. But now notice it's on the other side of the graph. Now as x gets bigger, the y values get closer and closer to 0. And then we still have a y-intercept at 0, C. So this is the general shape of an exponential curve. Depending on your base, when a is bigger than 1, we get something called an exponential growth model. That means that the function is increasing as x increases. Or if your base, your a value is between 0 and 1, you get something called an exponential decay model. That means the function is decreasing as x increases. Okay, we can add this basic function graph to our list of basic functions that we should kind of know. We should know what a line looks like, the identity function. We should know what x squared looks like. We should know what x cubed, the square root of x, the cubed root, polynomial. Those are things we talked about back in chapter 2. Now we should also know what an exponential function looks like. All right, I want to do an actual example of an exponential growth model really quickly. Let's look at f of x equals 2 to the x. That one's easy and easy to graph. We're going to start off by making a table of values to come up with points on the graph. And then we're going to plot the points and sketch the graph. And it should look like the exponential growth curve that we had before. All right, so let's go with the points. Where should I start? 3, 2, give myself a little bit more room. We'll go from -3 to 3. 3, 2, 1, 0, -1, -2, -3. These are the values we're going to plug in for x. Then we're going to find y, and that'll give us an ordered pair or a point on the graph. When x is 3, 2 to the 3rd power is 8. So we get the point 3, 8. When x is 2, 2 squared is 4. So the point 2, 4 is on the graph of this function. When we get 1, 2 to the 1st power is 2. So 1, 2 is a point. And then when we plug in 0, remember, plugging in 0 for x gives you your y-intercept, which if you look at the function, we just have 2 to the x. So our c value here would just be 1 because there's no other number written in front. So 2 to the 0 power does indeed equal 1. 0, 1 is a point on the graph. And then pay attention here to our negative exponents. This kind of shows why we get that horizontal asymptote at the x-axis. When we plug in -1, 2 to the negative first power is 1/2. So -1, 1/2 is a point. And then what happens if we get more negative? 2 to the negative second power, that's 1/4. So we get a smaller number because 1/4 is smaller than 1/2, but it's still bigger than 0. So -2, 1/4. And then 2 to the negative third power, this would be 1/8. So the more negative you get, your outputs become smaller and smaller, but they never actually get negative. They just get closer and closer to 0. Okay, now for the fun part. You get to sketch this. All right, so if this is our x, this is our y. For the x's, we did 1, 2, and 3. And then -1, -2, -3. And for our y's, we need them to go to at least 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, now let's plot these points. The first one's 3, 8, which boom, 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 boom. Ta-da, there's 3, 8. And then the next one's 2, 4. 2, 4 is here. And then the next one's 1, 2. 1, 2 is here. And then we have 0, 1. And then for our negatives, I'll try to draw these as close as possible. -1, 1/2 would be about here. And then -2, 1/4. Ooh, it's real close to the x-axis. And then -3, 1/8 is even closer to the x-axis. All right, then putting these all together, I'll draw it in blue. I connect all of these. Notice the graph starts off very close to the x-axis. And then as x increases, the function increases itself. The y values increase. They start getting bigger and bigger and bigger. And if we were to go to the next value, when x is 4, y is 16. So it'll be even higher here. And as you can see, we get an exponential curve. And it's an exponential growth because our base 2 is bigger than 1. All right. Now this is just to show you an actual example that matches up with the general graphs that we put in did in the beginning. Any questions about this so far? All right, y'all. Well, next I want to talk about how we can shift these basic graphs. So what if I wanted to take this graph and shift it up 5 units or down 3 units or to the left 2 units or to the right 1 unit? How can we do that? We talked about shifts of graphs before. Good news, the rules that we learned before still apply for exponential functions. But the way the function looks is a little bit different, but we'll go through the examples. All right, so we are on shifts of exponential functions. So if you think back to what we learned previously in chapter 2, we said if we want to shift a graph vertically, that's up or down, we want to add a number or subtract a number from the entire function. That still applies. So if we had a to the x plus, I'll call it k. Take the function a to the x and add some number k to it. This shifts the graph up k units. And if we have a to the x and we subtract k from this entire function, that would shift the graph down k units. So just like before, to shift up, you add a number to the entire function. To shift down, you subtract a number from the entire function. Then remember, for shifting left and right, we add or subtract a number from the x. And this time the x is in our exponent. So if we have a to the x minus k, so we're shifting or subtracting a number from our exponent. Subtracting from the x will shift our graph to the right, k units. So this shifts right, k units. And lastly, we have a to the x plus k. We're adding a constant to the exponent. This is going to shift left, k units. All right. So for our next example, we are going to use this terminology, left, right, up, and down, or shifts left, right, up, or down, to compare a few functions to the graph of 2 to the x, the one that we just used. So compare the following to the graph of y equals 2 to the x. We'll look at 4 things. First, 2 to the x plus 3 power. Second, we'll look at 2 to the x and minus 3 from the entire function. And then we'll look at 2 to the x power and plus 5 for the entire function. And then lastly, 2 to the x minus 1. All right. So let me get a new color. For the first one, 2 to the x plus 3. We're adding a 3 to the x in the exponent. Remember, adding a number to the exponent means that we're shifting left or right. I'm sorry, means that we're shifting left since we're adding. So adding a 3, this would be the graph of 2 to the x shifted left 3 units. So adding a 3 to the exponent will shift our graph left 3 units. Okay, then right under that, 2 to the x minus 3, notice that 3 is being subtracted not just from the x, but from 2 to the x, from the entire function. Subtracting a number from the entire function shifts the graph down. So this is the graph of, or for part B, we get the graph of 2 to the x shifted down 3 units. All right. For part C, 2 to the x plus 5, we're adding that 5 to the entire function. So that's going to shift our graph up 2 units. So this would be the graph of 2 to the x shifted up 2 units. Oh, I'm sorry, not 2, 5 units. And then last one, we're subtracting 1 from the exponent. So 2 to the x minus 1. If we subtract that 1 from the x, that's going to shift our graph to the right 2 units. So we start with the graph of 2 to the x and then shift right 1 unit. All right. So hopefully this feels a little familiar to you because we've talked about shifts of graphs before, and it works the same way with exponential functions. Adding or subtracting a number to the entire function shifts up or down, and then adding or subtracting a number from the x, which is in the exponent, shifts left or right. It should also be noted, if you shift a graph up or down, that's also going to change your range and where your y-intercept is. And if you shift left and right, that also changes where your y-intercept is. Won't change the range though. Okay. All right, next thing I want to discuss, applications of word problems. I'm sorry, of exponential functions. So one application of an exponential function that we see often is with compound interest. So I just want to write out the two compound interest formulas that we have. Some of you may have seen this before in previous classes. We'll talk about what they mean today for our class. And then we'll also talk about them again in chapter 6. So you'll see these formulas a lot. So compound interest. First, what is that? So when you invest money, say in a savings account or at a bank, you're usually offered an interest rate. And let's say they say, okay, here, you can invest your money here at 10% interest. That's very high. Nobody's going to give you 10% interest. But for the sake of this example, let's say we're doing 10% interest. How much money will you end up having at the end of the year? That depends on how often your interest is compounded. That means how often is the interest being added to the account? So I know I'm earning 10% interest. Do I earn that 10% and does it get added to my account every day, every week, every year, every second? How does that work? So that's called the compounding frequency. And let's just do a quick example. I'll use easy numbers. $100 is invested at 10% interest for 1 year. And we'll look at two different cases so you can kind of understand what the compounding does. Let's say we compound once a year. So interest is compounded annually. That just means at the end of every year. Okay, so in this case, if we compound our interest at the end of the year, that means, let's just assume we put our money in on January 1st. We do not touch this $100. We just let it sit there and earn interest in the account. At the end of the year, the money that's been in the account for the entire year will earn 10% interest. So for year 1, we go in with $100, and then at the end of the year, we add 10% of 100. I picked these nice numbers because it's easy. What's 10% of 100? $10. So at the end of the year, you end up with $110. That's nice. Life's great. Okay. I feel like I should go on for another year. Ooh, okay. I'm going to change this. Let's make it 2 years. All right. Then for year 2, how much money do we go into year 2 with? We go into year 2 with $110 in our account. And then at the end of year 2, we earn 10% interest, not just on the $100 that we invested, but also on the 10% interest that we earned from the previous year. So you earn 10% of however much money you had in the account for that year. So this time we're earned 10% of 110. 10% of 110 is $11. So you end up with, let's see, $121. All right. So one thing I want us to notice here is instead of just instead of just adding 10% or $10 every year that the money is in the account, with compound interest, not only do you earn interest on the amount that you invested, the $100, you also start earning interest on the interest that you earn. So it's compounding, building up over time. Okay. Now that's if we compound annually. If we compound it, let's say, semi-annually. That means twice a year, okay? So instead of waiting to get your interest at the end of the year, you get your interest added to the account every 6 months. So after 6 months, the $100 that's in your account, instead of earning 10% at the end of the year, you're going to earn half of that, 5% every 6 months. Does that make sense? So you take your 10% interest for the year, and you got to break it up. 5% for 6 months and 5% for the next 6 months. Okay, so you'll get $100 plus $5, which is equal to $105. I want to put a little note here. Semi-annually means twice a year. So 5% every 6 months. All right, so after 6 months, we have $105. Cool, that's nice, $5 free. Then going into the second 6 months, so after 12 months or after 1 year, you're going to this with $105, and then we earn 5%, I'm sorry, of $105. So you can calculate that. 105 times 1.05. I'm sorry, I calculated something that I didn't want to calculate. 105 times 0.05. That's $5.25. So we end up with $110.25. Now, this is where I want to point out something important. After 1 year, in both of these cases, you essentially earn 10% interest. The first year, you just earn 10% at the end of the year. In the second case, you earn 5% every 6 months. So together, that's 10% interest, right? Notice, though, that you end up earning more, in the second case. When you compound more frequently, you earn a little bit more money. Now, you might be thinking that's not a lot of money, it's just a quarter. But if you're dealing with bigger sums of money, every little penny counts. So the more frequently you compound your interest, basically that $5 that we earned in the first 6 months, we started earning interest on that earlier. So that's put into our account now, and now it can start earning interest too. So the more frequently you compound your interest, the more money you get. And we can continue this for the next year as well. If you go on to the next 6 months, that's after 18 months. We go into that period with $110.25. And then if we add 5% to that, 110.25 times 0.05, that's $5.51. It's really 51.25 cents. Okay. So what's that? 115.76. All right. And then after 2 years, we know in the first example, we ended up with $121 after 2 years. In this case, if we take our 115.76 and add 5% to that, that's adding $5.79. Then we end up with $121.55. Look at there. So the moral of the story is there are two morals to my story. One, this is how compound interest works. You invest money into an account, you keep it there, and then you earn interest at the end of the period. And then you start earning interest on that interest for the next period. Okay, so you earn interest on your interest. It's compounding. That's wonderful. And then also, as far as the compounding frequency, you can compound your money annually. That means you add the interest at the end of the year. Semi-annually, that means you add the interest at the end of every 6 months. Quarterly, That means you add the interest at the end of every quarter, 3 months. Weekly, you add the interest at the end of every week. So of course you can start compounding more frequently, because as you can see, the more often you compound, the more money you get. All right, so the more often you compound your interest, the more money you end up with at the end. So next page, we have a formula for finding this. You don't have to actually do this by hand. The compound interest formula. It's P equals, hold on. Let me make sure I'm using the same terminology our book uses. I'm sorry. We use S. S equals P times 1 plus R over N to the NT power. P is called the principal. That's the initial amount of money that you invest. R is the interest rate as a decimal. T is the time in years. And N is the compounding frequency, so the number of times you compound per year. So in our case, when we compounded annually, N would be 1. You compound semi-annually, N would be 2, and so on. You compound weekly, N would be 52. And then there's one last formula that we need to learn, and we'll do a couple of examples like this. Last formula, if you are compounding, well, if you think about the last example, we said the more often you compound your interest, the more money you get. So someone thought, well, what if I compound every day or every minute or every second? Is there like an upper bound to the amount of money that I can get? There is. If you compound your money, something called continuously, we actually end up with a slightly different formula for continuously compounding interest. That means that your money or your interest is being added to your account all the time. So for continuous compounding interest, we get the formula S equals P times the number E to the RT power, where P is the principal still, R is the interest rate as the decimal, and T is still your time in years. The difference in this case is if you're compounding your interest all the time, there is no N. N is infinite. You're always compounding, so you don't need that number. And remember, E is the number E. So a quick example. Let's say if $3,000 is invested at 4.5% interest, compounded quarterly, how much is in the account? After 5 years. So this means we put $3,000 into an account for 5 years, we just let it sit there. During those 5 years, the $3,000 is earning interest. Yay. How is it earning interest? Every quarter, the interest is added to the account. Okay. To solve this problem, since we're compounding quarterly, we're going to use the regular compounding interest formula. You only use the continuous compounding interest formula if it says continuous in the problem. Okay, so here we're going to use S equals, I'll write it over here, S equals P times 1 plus R over N to the NT. S is the amount that we end up with at the end. P in this case would be 3,000. R in this case is the interest rate, 4.5%. You want to convert that to a decimal though, so 0.045. We are compounding quarterly, so our value of N, quarterly means 4 times a year. N is 4. And then T, we're doing this for 5 years, so T is 5. Then we just plug this into the formula. P times 1 plus 0.0, oh wait, why did I say P? Sorry, guys. 3,000 times 1 plus 0.045 over 4 to the 4 times 5 power. And then, of course, you need a calculator to do this. If you want to, some people like to simplify the base, 1 plus 0.045 to the 4th power. If you want to, you can do that if you get a terminating decimal. In this case, this would simplify to 3,000 times 1.01125 to the 20th power. So now hopefully you can see that this is an exponential function. The base is 1.01125. The C value would be 3,000. So you start with $3,000 and then it grows after that. All right, let's put this into our calculators. 3,000 times 1 plus 0.045 over 4 raised to the 20th power. After 5 years, we'd end up with $3,752. And since we're dealing with money, we'll round 2 decimal places, 25 cents. All right, cool, not bad. However, what if we wanted to know how much, like what's the maximum amount of money we can make? What if we compound our interest all the time? Okay, so if the interest rate is 4.5%, we're keeping the money in the account for 5 years, we're investing $3,000, but instead of compounding quarterly, we compound continuously. How much money will we end up with? Okay, that's the next problem we're gonna do. All right, so we'll do same problem, except instead of compounding quarterly, we're compounding continuously. That's part B. What did I call it? Part A in the last one? No, I didn't. All right, so this time we'll do $3,000 invested at 4.5% compounded continuously. For 5 years. Okay, this time, when you see compounded continuously, and only when you see continuously, use S equals PE to the RT. In this case, P is still 3,000. E is the number E. So we're not gonna plug in anything for E, it's its own number, it's a constant. And then R in this case is 0.045, and then T is 5. So we have 3,000 times e to the 0.045 times 5 power. On your calculators, you should have an e to the x button. It's usually near the ln button. If you have a TI-84, it's going to be on the left side next to like the 7 or 4. Okay, so we'll type in 3,000 and then e to the 0.045 times 5 power. This would be $3,756.97. Comparing this to the number we got when we compound quarterly. When you compound quarterly, you got $3,752 about. When you compound continuously, you get $3,756. So you end up with a little bit more money when you compound continuously. We're going to spend the rest of the class talking about the inverse of an exponential function, which is called a logarithmic function. All right, then section 5.2 discusses logarithmic functions. And again, a logarithmic function is the inverse of an exponential function, and I'll kind of try to explain what that means in just a second. We'll start off with a definition here. So first, just like exponential functions have a base, a number that we're raising to the x power, log functions also have a base. Here's the difference. With exponential functions, we say, here's my base. I want to raise it to this power. What do I get? So, okay, what's 2 to the 4th power? That's exponential. We say, oh, 2 to the 4th power is 16. With exponential functions, you know the base, you plug in something for the exponent, you get out an answer. You're finding the output. Logarithmic functions are the opposite of that. You know the base, you know the output, but logarithms help you solve for the exponent. So just a really quick example. Let's say we had something like 2 to what power equals 8. A logarithmic function would help us solve something like this. It would help us solve for the exponent. So we know what our base is. We know what the output is that we want. What exponent do I need to get this? That's what logarithms are. They help us solve for the exponent when we know our base and we know our output. Okay, so definitions. We still have the same conditions for our base for a greater than 0 and a not equal to 1. The logarithmic function is, first is denoted, y equals log base a of x. So this is red, y equals log base a of x. This is not log of a to the x power. Not that, not that. It's log base a of x, okay? And what does this mean? So the log function is this, and this means if y equals log base a of x, y equals log base a of x, then a, our base, to the y power is equal to x. So log base a, the base tells us, I'm sorry, the a tells us what our base is. The x tells us what output we want. And then the y, or the answer that we get for the logarithm, is the exponent. Okay? And a quick little note about the domain, and then I'll do an example. Note the domain of a log function, or log base a of x, is x has to be greater than 0. Or in interval notation, 0 to infinity. All right, so I have my little example at the top, 2 to the x equals 8. The logarithmic form of that would be log base 2 of 8. So log base 2 of 8, what does this mean? Means what power should I raise 2 to in order to get an output of 8? So we know the base, we know what output we want, we're trying to solve for the exponent. So log base 2 of 8 equals x. This is the same as saying 2 to the x power equals 8. Every logarithmic equation is equivalent to some exponential equation where we're trying to solve for x, the exponent, okay? So in this case, what power would I raise 2 to get 8? We know that 2 to the 3rd power is equal to the 8. So we would say log base 2 of 8 is 3. So essentially, logarithms, like I said, they're the inverse of exponential functions, because instead of trying to find the output, we're trying to find the exponent, right? But essentially, they're not the same thing, but they're very connected. We're taking an exponential equation and we're solving for the exponent. Logarithms equal the exponent of the exponential equation. Okay, I want to take a moment. It's 9:32. How much can we do? I want to talk about the graph of a log function really quickly, and then we will stop there. There are lots of properties of logs. We'll continue with this section in the next class. Okay, so graph of a log function. Example, let's graph, for exponential functions, we graphed 2 to the x, so let's graph the inverse of that, which is y equals log base 2 of x. So basically, I'm going to plug in numbers for x. Those will be my outputs, and I have to figure out what exponent I raise 2 to get that output. Okay, I'm going to pick my x values here very strategically. Basically, I'm just going to pick powers of x. All right. So let's go 8, 4, 2, 1. Remember, we said when we're taking the log of a number, we can't take the log of a negative number. It has to be positive. So we can look at some fractions though. 1/2, 1/4, and 1/8. So the first one, which we just did, log base 2 of 8. This is asking what power do I raise 2 to get 8? That's 3. So we get the point 8, 3 for our graph. Next one, log base 2 of 4. What power would I raise 2 to get 4? That would be the second power. Okay, so we would say 4, 2 is a point on the graph. Next one, log base 2 of 2. 2 to the first power is 2, so this should be equal to 1. And we get the point 2, 1. Next one, log base 2 of 1. This is asking what power can I raise 2 to get 1? Remember, anything raised to the 0 power is 1. So this would be 0. And we get the point 1, 0. Next one, log base 2 of 1/2. That would be -1. Log base 2 of 1/4 would be -2. And log base 2 of 1/8 would be -3. And remember, the way I'm getting these answers is to think about the exponential form. This means 2 to the -3rd power equals 1/8. That's true. That's how I know my exponent needs to be -3, which means the logarithm equals -3. All right, so the last few points here are 1/2, -1, 1/4, -2, and they erase that, 1/8, -3. So to graph this, my x values are going to be positive, bigger than 0. And then the y values here are going between 3 and -3. So our graph is going to look like this. This is our x-axis. Here's our y-axis. And let me try to plot these points. The x's are between 0 and 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I missed. Okay, sorry. 6, 8. And then for our y's, they were between -3 and 3. 1, 2, 3. 1, 2, 3. All right, let's plot. First, we get the point 8, 3, which would be up here. Then we had 4, 2, which would be about here. 2, 1, it's about here. Then notice we have an x-intercept this time at 1, 0. And then we get numbers that get really, really close to the y-axis. 1/2, -1. 1/4, -2. And 1/8, -3. Ooh, that's really close to this axis. It's not actually going to touch it though. 1/8 is really small, but it's not equal to 0. if we connect these, look at what's happening. We get a graph that's really close to the y-axis, and then it increases, but it starts to curve downward. It's increasing kind of slowly, but still increasing nonetheless. This is the general shape of a logarithmic function. I'm going to write out, and we'll finish here, the domain, the range, the intercepts, and the asymptotes for a logarithmic function. And then you can notice the differences between logarithmic functions and exponential functions. Everything's kind of opposite. So I'll write it out here and then generally. So for this function, notice the domain, we said, has to be greater than 0. So 0 to infinity. The range here, which would be the possible outputs, the graph is going to continue increasing, so the y values will keep going up, and the graph keeps going down and closer to the y-axis. So our range is actually all row numbers. We can get out anything, okay? This time, instead of having a horizontal asymptote, because we cross the x-axis, we actually get a vertical asymptote. And the vertical asymptote is at the y-axis, x equals 0. And last thing, instead of having a y-intercept, we get an x-intercept. And the x-intercept was at 1, 0. This is true for any log function of the form log base a of x if a is bigger than 1. All right, now I'm going to wrap up by just drawing out these general graphs really quickly for log functions. You know, for exponential functions, we said, oh, we have an exponential growth when a is bigger than 1 and an exponential decay when a is between 0 and 1. What do the graphs look like for log functions? All right, so we want the graph of log base a of x for a greater than 1. It's the graph that we just saw. So we'll have a vertical asymptote at the y-axis, and then our graph will increase slowly. That's x, that's y. If we have log base a of x for a between the 0 and 1, we get this graph, but reflected across the x-axis. So instead of starting off all the way at the bottom, we start off at the top and then decrease slowly and slowly and slowly. Oh, that one's bad. I'm trying again. And in both cases, this point would be 1, 0. And in both cases, the domain is 0 to infinity. The range is -infinity to infinity. We have a vertical asymptote at the line x equals 0. And the x-intercept is 1, 0. And the last thing I'm going to do, I know I keep saying it's the last thing, but I'm for real this time. I'm going to go on to Desmos, and I just want to show you guys the graph of 2 to the x, and then its inverse, log base 2 of x together. And we'll see how they compare to each other. They're actually a reflection over the line y equals x. So that is where we're going to stop. All right, so I'm just going to stop sharing here and then go on to Desmos. Share my screen. All right, and we're going to look at 2 raised to the, not squared, 2 raised to the x power. That looks like the graph we saw earlier. It's an exponential growth. And then we also want to look at, I have to find it, the log function. Log base 2 of x. So the red curve is the exponential function 2 to the x. And the blue curve is its inverse, the log function, log base 2 of x. And then one last thing I'm going to graph, the line y equals x. I can find the equal sign. There we go. Y equals x. If you look at the red curve and the blue curve, if you reflect the red graph over the green line, you get the blue graph. So that's how inverse functions work in their graphs. Yeah, basically they are opposites. The domain of the exponential function is the range of the logarithmic function, and the range of the exponential function is the domain of the logarithmic function. The exponential function has a horizontal asymptote. The logarithmic function has a vertical asymptote. The exponential function has a y-intercept. The log function has an x-intercept. They're inverses or opposites of each other. All right, I'm stopping for real now. Last thing for your lab today. We didn't quite get to all of the properties of logarithms that are in section 5.2. We'll continue with that in the next class. But you should be able to do this first part for sure, where you're comparing different exponential functions in their graphs. For problem number 2, it's a continuous compounding interest problem. You should definitely be able to do that. I would like you to try problem number 3. It's a regression problem. We talked about exponential regression back in chapters 1 and 2. We did like a linear regression problem, and I think we did a quadratic or a power regression problem before. Try to do this with Excel. We'll definitely go over this lab at the beginning of the next class. And then the rest of these problems are just practicing rewriting logarithmic expressions in exponential form. We're going to do a lot more practice with this in the next problem, but just try the problems and see if you can get them. Get as far as you can on this. I know definitely for problems 4, 5, 6, and 7, we didn't do a lot of practice with that today, because in the next class, we're going to practice a lot more with 5.2.